Hello. So in today's video, we are going to discuss how to write chemical equations from carbon skeleton structures, and then we're gonna be finding the delta E, which is the change in energy from the bonds that are being broken and formed, and then from that we're gonna predict the delta H and the delta H, S for the reaction, and then determine if the reaction is at equilibrium, and if not, what the direction of the reaction will be. And then we'll be finding the partial pressure of equilibrium using the ICE table, and then we're gonna be able to determine the effects of change in temperature in a reaction, and we're gonna do this using the Le Chatelier's principle. So in the question, we're given this equation. So in a carbon, this is what we call a carbon skeleton, where a line represent in each end there is a carbon. So in determining what the chemical equation for this will be, we have to put a carbon at the end of each line. So there's a carbon here, there's a carbon here, a carbon there, a carbon there, and a carbon there, and a carbon there. And that's for the first reactants, is we're reacting 1, 2, 3, 4. So we have 4 carbons, right? So it's C4. So it's C4. But then remember, carbon needs 4 bonds so that it can be in octet, so that it's stable, right? So in this carbon has 1, 2, 3, 4. So that needs 2 hydrogens. So for it to be full, for it to be stable. So in this C, we have 2 hydrogens, right? From that C. And then this C has 1, 2, 3, and it's 1 more bond, and that will be bonded into 1 hydrogen. So that's 3 hydrogens, right? So we have 1, 2, 3 hydrogens, and then this carbon has 1, 2, 3, so it needs one more hydrogen, so that it's stable, and that's 4 total hydrogens. So we have 1, 2, 3, and 4. And then our last carbon from this structure is that carbon, right? And it has 1, 2, 3, 4. So it needs 2 more. So we already have 4 carbons. So it's 1, 2, 3, 4, 5, and 6. So in total we have 6 carbons, which I actually represented here. So you can see how this, from just this, we can get this. Just knowing that in each end of a line there's a carbon, and a carbon needs 4 bonds to be stable, right? And hence you fill up the other gaps with hydrogens. And so our first structure is C4H6, and we're now told the state of the reaction, but we are going to assume it's gases, because in the equation, in one of the questions, we're supposed to find partial pressure, and partial pressure is basically going to be involving either gases or aqueous solutions. But in this case, we're gonna assume it's gases. Okay, so we're not yet done. So we have C4H6 reacting with this other molecule. So from this, we get this, right? And we know that in each end we have a carbon, but these are like double bonds. So in each end we have in each end of the two, we only have 1 carbon, and a carbon needs 4 bonds. So that carbon already has 1, 2. So we only need 2 more. So 1, 2, 3, 4. And then these 2 bonds are bonded to hydrogen, same as the other one. So it's C, 1, 2, 3, and 4. So 2 hydrogens, right? And so we get this structure, which is C2 H4, and it's a gas. And then and this is our equation sign, and then we get this structure. So we just fill each corner with a C, and we have, when I filled it, I got 1, 2, 3, 4, 5, 6. So it's C6. And how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 hydrogens. So we now have an equation. We now have an equation which is C4H6 plus C2H4 reacts to give us C6H10. So from here we're done with the first objective. So we can cross it out. I'm gonna cross it out. Oops. Okay, there we go. So first objective done. So let us now determine the delta E. So in order to find the delta E, we have to identify what bonds are being broken and what bonds are being made. So from here, we see that this double bond is kind of like broken up, and that is represented with 1, with that kind of bond. And then we have one of this double bond is broken, and it forms one of the bonds, it forms a bond between this and that. And then we have this, the shifting of this double bond here. So with the breaking of the bonds, as I have highlighted in this little purple boxes, is that we'll be breaking 3 C to C bonds. Those are the bonds that we're breaking. And from like a thermodynamic, the thermodynamic chart that indicates the energy of bonds. Actually, that's wrong. C to C double bond is 611 kilojoule per moles. So the total energy of the bonds that is broken is going to be 3 times 611 kilojoules per mole, and you get 1,800 kilojoule per mole, right? And so let's see how many bonds are being made. So after breaking this double bond moves here. One of the bonds move here and makes a double bond. So we are making 1 C to C double bond, and then we broke these two double bonds, and we are forming 1 and 2. So we are forming that single bond and that single bond. So we are forming 2 C to C bonds. So what is the total energy of the bonds being made? So we have a C to C bond is 350, and it contains 350 energy kilojoule per mole. And so we're gonna multiply 2 times 350 plus the C double bonded C double bond C, which is 611, and adding those two, I have 1,311. So how do we get the changing energy? So the changing energy will be the energy of bonds formed minus the energy of the bonds being broken, right? So we get 1,311 minus 1,833. And you get, from that you get a negative 522 kilojoule per mole. So our change in energy is negative. So that means that this reaction is an exothermic reaction, making our delta H to be negative and our delta H to be less than 0. So this is basically being represented by a chart. This means that even looking at this energies, is that our reactants are high up in energy than our products, and that means our products that are producing heat, which is going to be absorbed by the surrounding of the system. And that's why in an exothermic reaction, you feel the hotness, like when you touch something or a beaker that is containing an exothermic reaction, the beaker is going to feel hot. So like that, the products are losing that heat. So that's why the products are low in energy. Yeah. And so since we cannot find our structures in a delta S table, we are just gonna look at the structures. So we have two things that are reacting to form one thing. That means our entropy is decreasing, and that's gonna make our delta S to be less than 0 because we have more order in the products. And so we have determined our delta E and predicted the delta H and delta S of the reaction. So now let us determine if our reaction is at equilibrium, and if not, what will be the direction of this reaction. So at equilibrium, Q equals K. And in this question, we've been asked, is C4H6G reacting with 1 molar of C2H4 produce C6H10? Let me reword that. Is C4H6 reacting with C2H4 to form C6H10 at equilibrium in 850 Kelvin temperature? And we are given the K. So the equilibrium constant is 5.6, and we are given the partial pressure of C4H6, C2H4, and we're given the C6H10. So we're going to be using this equation whereby in a reaction of A plus B to give us C, our Q pressure is going to be pressure, and then C over P A small a, then P B small b. So, and the small letters represent the coefficients, as you can see there. And so all we gotta do is plug in our information. So PC is the partial pressure of C6H10, and that's going to be 0.200, and the coefficient is 1. And then for A, it's C4. So this is our A, that's our B, and that's our C. And then the C4H6 is 0.200 times 0.100, and all their coefficients are all 1. So we get our Q to be 10. And 10 is way greater than 5.7. So our equation is definitely not at equilibrium. We can see that our Q is way greater than our K. And so what this reaction will do, so that at equilibrium, remember at equilibrium, Q equals K. So this reaction will have to move backwards in order Q to be here, so that the reaction is at equilibrium. So if we're moving backwards, that means we're losing this but adding more of this, and we're gonna see how that information is important while finding the partial pressure. Okay, so how can we find the partial pressure? And this we can do it using the ICE table. So the ICE table is a table that helps us find like the partial pressure or concentrations at equilibrium. At first, we start with initial concentration, hence the I, and then we plug in the predictions of the change, which is represented by C, and then that's by combining both of them, the initial and the change, we are able to find the concentration or the partial pressure at equilibrium, represented by E. So let's first represent our equation in this table. So C4H6, we started off with 0.200 partial pressure. So it's like ATM or bar. Our units are in bar. So it's 0.200. And then our initial concentration of C2H4 is 0.100, and our concentration for C6H10 is 0.200. And remember, we identified that our reaction will be moving backwards, right? So this we'll be losing this but getting more of this. So our change is gonna be minus X, because we're losing C6H4, but we're adding reactants. So each of them is plus X. And that is plus X because our coefficients is 1. So it would be like plus 1X, plus 1X, plus 1X, minus 1X, sorry. And now we combine those. So in our at equilibrium, we're gonna take the initial concentration and we're gonna add our change, which we're gonna find using the quadratic formula, and then our change for C2 at equilibrium C2H4 will be 0.100 plus the change, and then C6H10 is going to be 0.200 minus X. And what equation do we use to solve that? We're going to use the equilibrium constant equals the pressure of the products divided by the pressure of the reactants. And at equilibrium, the Kp is 5.7, so it's 5.7, and then we plug everything in this equation. So it's going to be 0.200 minus X, and then divided by 0.200 plus X times 0.100 plus X. And then we solved our denominator, and we got X squared plus 0. If we multiply this, we get X squared plus 0.300X plus 0.27. And then what I did is I multiplied both sides with this. So I multiplied times X squared plus 0.300 plus 0.02. And you see how that cancels? And then on this side, I also multiplied with this. So I get something that is like that. So it's 5.7 times X squared plus 0.300 plus 0.02 equals, remember, that is still there, equals 0.200 minus X. And I open my brackets by distributing the 5.7, so it'd be 5.7 times X, 5.7 times 0.300, and then 5.7 times 0.02, and I get 5.7x squared plus 1.71 x plus 0.114 equals 0.200 minus x. And I brought both of this to this side. It's so I brought 5.7x squared plus 1.71x, and then I brought this to this side and becomes positive, so it's plus X. And then I have plus 0.114, and then if I bring this to the other side, since it's positive, it's going to be negative, and that will be equals to 0. And when we solve this equation, it's going to help us use the quadratic formula. And combining all of this, putting the like terms together, and adding what needs to be added and subtracting what needs to be subtracted, I got 5.7x squared plus 2.71 minus 0.086 equals to 0. And now we are able to plug our information into the quadratic formula, because we have our A, we have B, and we have C. So I plugged everything in here, and I solved that using a calculator, and I got two x values, and I got x equals 0 0.0300, and x equals to minus 0 0.500. Of course, we're gonna pick the first one because our x cannot be 0. We cannot, yeah, we cannot, it cannot be less than 0, I'm gonna say, because we need to have some change, and we identified that there is going to be change. So if it's negative and it's less than 0, that means that no change happened, or the reaction is not working as it's supposed to. So we got our x, and it's time to plug our x into the equilibrium concentrations that we identified using the ice table. So at equilibrium, we identified that C4H6 is going to be 0.200 plus x. And so we substitute the x with 0.0300, and we got 0.230 bar. For C2H4, it's 0.100 plus the x, which is 0.030, and I got 0.130 bar. And then C6H10 is 0.200 minus 0.030. You get 0.17 bar. So at equilibrium, we have these concentrations of our equations. I mean, pressure. We have these pressures of these gases. Alright, so we finished our third and fourth objective. We determined if our reaction was at equilibrium and the direction of our reaction, and we found the partial pressure using the ice table at equilibrium. So now let's determine the effects of change in temperature in the reaction, and I'm gonna explain that using the Le Chatelier's principle. So in the effects of pressure, we're gonna be determining whether we can reverse this reaction. So remember, our reaction is proceeding backwards. So is there a way that we could get our reaction to move forward by manipulating the temperature? And in that case, if we can, and it's yes, we can reverse the reaction by manipulating the temperature. But now the question is, do we need to rise or lower the temperature? And an important information that we need for this is what's the nature of our reaction? Is it an exothermic or an endothermic? And remember, we identified our reaction to be exothermic. That means in addition to the C6H10, we're also producing heat. So we get this reaction, C4H6 plus C2H4, C6H10 plus heat. So I use these different colors. The black one means that our reaction is going backwards, but we need to reverse them. So we need to look for an equation that gives us this kind of arrows. So what is the effect of increasing temperature? So when we increase temperature, the prediction is that our reaction is still going to proceed backwards. Why is it? So Le Chatelier's principle says that when a change is applied to a system, the reaction will proceed in the direction that minimizes the disturbance or the change. So remember, this is an exothermic reaction. So we are producing heat. So adding the heat, it's not, the reaction is not gonna wanna produce more heat because we're already adding heat. And so that means our reaction will move backwards where no heat is being produced. And since if the forward reaction is exothermic, the backwards reaction is endothermic. So it will use this heat that is produced, that is already produced, to form more C4H6. So that means when we increase the temperature, our products and the heat being produced is going to decrease. And that's going to increase our reactants. So our reaction still proceeds backwards. So by increasing the temperature, we have not reversed our reaction. And this is mainly because of the nature, because it's an exothermic reaction. What about decreasing a temperature? So, if we lower the temperature, we're gonna want to increase the temperature. So we're gonna be producing more products, which is products plus heat. So the reaction, when we lower the temperature, the reaction will move forward, and we have successfully reversed the reaction, because when we lower temperature, we increase the products and the heat, and that decreases our reactants, and that is a forward reaction, and we have successfully reversed a reaction. If we go back to the thermodynamics table predicting the delta G and the spontaneity of a reaction, we can identify. We can conclude that at low temperature, our reaction is spontaneous, right? And remember what we predicted about delta S and delta H? We predicted that our delta H is less than 0, so less than 0, and our delta S is less than 0. So that gives us this prediction where delta G is going to be it's going to be less than 0 at low temperatures, and delta G is going to be greater than 0 at high temperatures. And so if delta G is less than 0 at low temperatures, that's going to make a reaction to be spontaneous at low temperatures. And that echoes what we found here, that in low temperatures, our reaction is proceeding forward. And so we can conclude that by manipulating the temperature, we can attach and detach a particular molecule to form either products or reactants. So in this equation, I predicted that C2H4 can attach, detach, and retouch by breaking and making covalent bonds by influencing the temperature. So we can see how it's being attached to form the products, and how it can be detached to form the reactants. And that's the end of today's lesson. Goodbye.